Today our topic is source entropy. So we would discuss about the source entropy specifically, and we will go in details of this mathematical expression which actually gives or computes the source entropy, right? But before going to explain this expression and the diagram which is shown in this slide, this diagram, I would like to give you an example that why we need what information actually we get from the entropy of a system. In communication system, we usually take our data. We take our data from the source. So the source and the whole communication system targets to transmit the data of the source successfully to the destination, right? So the source of information is very important. The source of information is important for us in a communication system. And this source of information may be the information source may be the data or speech or video, right? The source may give you video, the source may give you data, the source may give you some speech, some audio, right? So all these sources of information are important for us, and we model this source as a random process. This source is actually a random process. Why we call it a random process? Because the data which we get from the source is actually random. Whether it is in the form of a text, or it is in the form of audio, or it is in the form of video, the data from the source, communication source, is usually random. You can take a simple example. Just consider an example of your class. You have almost 30 to 35 students, right? So if somebody of you make a call, then he would be just an information source, right? He would communicate to the other person, and every one of you who makes a call will have different data. It would have different speech, right? Some of you may be talking with your friends, some of you with your parents, or some of you may be talking with about your holidays, about your summer vacation. Some may be planning for the studies, some may be discussing some topic. So whatever you are discussing, that is actually, it depends on the source, and the source usually outputs random data. So we model the source as a random process. The same is true for text data. For example, you just if I ask you, your whole class, to write some story, every one of you will have a different idea, and he will write different text, right? And the sequence of his alphabets, right? If every one of you, suppose every one of you is writing a story of his own choice, so every one of you will have different idea. You may start differently, you may end differently, your words will be different. So all the sequence of alphabets which you would be using, suppose you are using the English language, right? So in English language you have the set of alphabets which I would represent by this set. Suppose I have this set. So in English language you have this set up to Z, right? Up to Z. So these are the 26 alphabets, right? 26 alphabets in this set. So you have, if you are writing your story using these alphabets, then the sequence of alphabets which you are writing would be different than the sequence from your colleague, from any other sequence of your colleague. Why? Because you would be writing differently according to your ideas. So maybe these alphabets, the arrangement of these alphabets in your text, right? Suppose you are writing some text, blah 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 blah, right? And you are writing something, and all the alphabets which appear in your text would be this sequence would be different than any other than your colleague. So it means if 100%, if thousands of people are writing different, if the task is assigned to 1,000 people that write a story with your own idea, your own choice, in the end we collect all those 1,000 stories and we try to find out the sequence of alphabets right from the beginning. You would find unique sequence for everyone, right? So if we go more deeply, if you can find unique sequence for everyone, and if we go in more details, right? Maybe somebody start the story, the sequence. You can have 1,000 sequences of these alphabets, right? So maybe in some story you would get letter A. Maybe some people have started with A. Some people have started their story with D. Some maybe with some other words. So everyone has a different sequence. For example, in this, letter A is the first one. For the second source, letter T is the first one. Letter H is the second one. Right. So this similarly for the third person, maybe amazing. The word, if somebody starts with the word amazing, so he has the first letter, the second letter is different, the third is different than other person. So the sequence is different. So it means the information or the data which we get from our random source is different, right? For every source it is different. So the data which we get from the information source is different. That is why we model our source as a random process. If we take the example of a text data, so the source one may have a different sequence of alphabets, maybe A, then T, then H, then E, then O, then P, something like this. The other source may have W first, R second, the third one, then this sequence. So every source, this may be from source number 1, this may be from information source number 2. So every source has a different sequence of these letters. However, all of those are using the same set of alphabets. If you are talking about the text, so all of them are using the same alphabets, right? Very important, very important. Now you know that there is a set of alphabets for the English language, similarly for Urdu language, and another important thing is when we say it's random, all the letters which appear in different texts are random. Actually, the source is giving you random alphabets, right? Each source gives you a random alphabet. You don't know what alphabet next will come for source number 1 and for source number 2 until he give you some sequence, right? So that is why our sources, a source of information are random. Our source of information are random. Now, when we say the source of information is random, each of these sequences from source 1, from source 2, and suppose 1,000 people are assigned, so you have text from 1,000 people, right? And if you now you can do some analysis. For example, you can find that in source number 1 how many times letter A appears. Similarly, you can just count letter A which appears in the first story. So that would give you the frequency of A in story number 1. Similarly, you can count letter A appearing in the second sequence, and it would give you the frequency of A in the second story. And if you repeat this process for 1000 stories, you would find the probability of A, alphabet A, in text, right? You can find the probability of alphabet A in text in general. Similarly, you can find the probability, the chance. And how do you find that chance? You just count how many times letter A appears in the first sequence, and the total number of letters you know. How many times letter A appears in the second sequence, and the total number of letters you know. So you just sum all the count. The letter A appears 100, for example, 100 times in the first sequence and 200 times in the second, and so on. Just you sum that count and divide by the total number of letters, and you find the probability of letter A in the text. Similarly, you can find the probability of letter B in the text data, right? Similarly, you can find the probability of letter Z in the text data. So each of these 26 letters, has different probability, and we would define that probability. We would say that, okay, letter A has some probability, which we can say letter A has some probability, and we say that probability of letter A. Similarly, probability of letter B. So we need this information because the probability of letter Z and probability letter C and probability of letter Z. So we can find all these probabilities if we have 1000 stories available from 1000 writers, and you would get some probabilities, right? You would get some probabilities. Now, based on these probabilities, if you have these probabilities, right, and you have this set X, you can define the entropy. And actually entropy is known as entropy is denoted by h of x, right? H of x, which is equal to the negative sum of probabilities of these alphabets, right? These alphabets, and the log of those probabilities, and the base is usually taken 2. And this is for all the alphabets x. That is why if you see over here, x belongs to this set X, right? This is the set of alphabets. So for every letter, X belongs to set X means for every X belongs to set S means for every letter. Now when we say X belongs to set X, we means for every letter you have to find this one. So if you have 26 letters, as you see in your set of alphabets, you have 26 letters. So it means for English language, if you want to find the entropy, which is denoted by h of x, right, which is denoted by h of x, it would have 26. This summation would have 26 combinations, you say, or 26 products, you can say, the 26 sums, actually the 26 summations of this product. For example, if I write it for English language, I would say probability of A and log 2 of probability of A. Similarly, plus probability of B that appears in this text, and log 2 of probability of B, and so on for all these letters, and so on for all these. You can write here plus so on probability of Z and log 2 probability of Z. So this would give you the if you compute this, this would give you the entropy of the text or the English language, the entropy of this language. And what actually the entropy, this is actually a number. If you calculate it, you probability of A, probability of B, probability of C, probability of letter Z. So all these, if you add up all these probabilities, they would be equal to 1, unity, right? The maximum probability is 1. So the probability of all these letters would be 1. But if you compute this h of x, which is the entropy, which is known as the entropy of the source or the entropy of the system, it gives you a number, and that number would represent the, if the base is 2, like log to the base 2, if the base is taken to be 2, so that number would represent the minimum number of bits, the minimum number of bits required, for each, the minimum number of bits required for each letter or for each alphabet, the minimum number of bits, which means that you need this entropy, whatever the number is given by this entropy, that would be a lower bound, minimum number of bits required to represent each alphabet of that system, right? Each alphabet. So this is actually a lower bound which gives you information that if you want to store these alphabets in memory, you may need at least these many bits for each letter. So you can compute the whole text, you can compute it for the whole text, that okay, if each letter has these many bits, then I have total letters, suppose 1 million letters. So these 1 million letters, for these 1 million letters I would need this much memory, right? So actually the entropy is important. When we discuss the when we want to measure the information, of a source. So it actually gives you the measure of information of the source, and this is just we will see with the help of an example that how we get how we use this number, which is called the entropy. It's of course a number which is called the entropy, and it gives you the minimum number of bits required to store each alphabet in memory, right? If the base log to the base 2 is taken. Now if you go to the literature, you may also find that sometimes it is said that entropy gives you the degree of uncertainty, the degree of uncertainty of information. So that is also true. It gives you, because it's the measure of information. So you, with this number entropy gives you that measure, that whether the how much certain is that particular event. Let's take an example. Let's try to understand this concept with the help of an example. If you consider the two cricket teams, right? The Pakistani national team which is a stronger team usually for T20. Suppose we are talking about T20, so Pakistan has a very good position in T20, and you have a team of your class, right? The cricket team, you make a cricket team, good players from your class, and you make a cricket team, and you say that okay, we set some date for a match, for a cricket match between the sixth semester of High Tech University and the Pakistani cricket team. So you can clearly, now the two teams, based on the strength of the two teams, you can clearly say that it is almost no chances for the sixth semester to win this match, right? Or you can say that the Pakistani team for sure they will win. So if you want to assign probabilities to the win probability, right, the win probability, so you would assign 100% probability, you may say, okay, 99, or if not 100, you would at least say okay, 99.9% probability. I would say that 99.9% chances are for Pakistani international cricket team, because it's a stronger team, right? And just 0.1% is the team for the sixth semester, suppose. So because you are sure about the based on the strength of the teams, you are sure about the result of the cricket match, the result of the event, right? Before the event has been occurred, you are sure about this. So if you assign the probabilities, if we say the win probability, and the win probability of the Pakistani team is denoted by P, right? P. So we say okay, 99.9% is the probability, which is 0.99, and then you have to assign the probability to another team, which we have taken the sixth semester. So you can say okay, 0.1%, right? 0.1%, right? So it's so if we assign 0.1% here, 0.1% here, so that could be 1 minus P, and you are dead sure that okay, this team is going to win. Now if you observe this, 99.9% means 0.99. so let me specifically write 0.99 here, right? Let me specifically write 0.99. So I would say okay, it's 0.99 is the probability that the other team would win, and 0.1% is the probability that the sixth semester team would win, right? So this, now you are dead sure about this event. So if you are dead sure about the event, it has almost no information. If somebody says that okay, there is a match between the Pakistani international cricket team and the sixth semester, so you have no information about the result, almost no information, right? Because you are dead sure about the result of the event. And if you see the same thing here on the entropy, on the entropy curve, this is actually the binary entropy curve. When you have two events such as this one, as we discussed here, when you have two events, so if the probability, this x-axis shows you P, right, and the y-axis gives you H, the entropy, binary entropy, HB, which is denoted by HB of P. So when you have 0.99 here, suppose P is 0.99, so it would be somewhere here. And if you, this 0.99, if you observe it on the vertical axis, right, you just, the black curve, you just project it vertically and observe on the vertical axis, and you would get something here, some point here, which means the entropy of the system is very low, almost approaching zero, the entropy, right? And because there is no information, so the entropy is zero. The entropy zero means this event does not give you any information, or the information is very low, almost zero, approaching zero. But if you have two cricket teams, for example, the sixth semester section A, and we say the sixth semester section B has a cricket match. So if you assign probabilities based on the strength of the two teams, you would say, okay, every team has the sixth semester A has the probability section A has the probability 0.5. So it means the win probability of section B is also 0.5, right? And your P is here, this point. Your P is this point. So if you project it on the vertical axis, you can see that you get the entropy of the system is 1. The entropy, actually you can, I will give you the expression for the binary entropy using this expression, generalized expression now. But let me try to explain this graph. So the entropy, if you have 0.5 and 0.5 probability, so the entropy of the system is 1, which means 100% information. The result is uncertain, completely uncertain. So if the event occurs, it would give you maximum information because both the events are equiprobable. Both have equal probability. Either anyone can win. Section A can win, section B can win, because both the teams are equally strong. They have same strength. So if the probability P is 0.5. So if you project it on the vertical axis and you see this black curve here on the horizontal axis, and the vertical axis is 1. This is giving you the entropy, and entropy says it's 1. 1 means 100%, right? So it's 100%. The result is, or you can say the result is uncertain. It 100% uncertain. So 0.5 probability gives you the 100% uncertainty. Yeah, you are not sure who will win. You are not sure who will win. So if the P, the probability in a binary, in case of binary entropy, in case of such events which have only two possible outputs, if the probability P increases, if the probability P is 0.5, it means 1 minus P. The other event, the P is 0.5, 1 minus P is also 0.5. So both the events can occur and both the events have equal probability. So at a certain time only one of the two events will occur. So it has maximum information. It will convey maximum information. This event would convey maximum information, and the entropy 1 represent that maximum information or the uncertainty, the degree of uncertainty, that it is maximum, it is uncertain, 100% uncertain what would be the result of the cricket match between section A and section B. Now if the probability increase, suppose the one of the team is stronger and you assign a higher probability of win to that team, suppose instead of 0.5 you say it's 0.8 because the team is stronger, so the 1 minus P would be 0.2. And if you project this 0.8, on this vertical axis, you would see here I have 0.8, and you would see a number, which is smaller, right? The entropy is, you will see a number which is smaller, this number, and this number, a smaller number, gives you information that there is the event is uncertain, but it is not 100% uncertain, right? Most probably team 1 will win, which has 0.8%, which has the probability of winning 0.8, and the other one has 0.2. So your binary entropy is a smaller number, and you are more certain now that okay, team A is going to win because it has 0.8 winning probability, right? So this is this number, this entropy, binary entropy, is a smaller number now, and it gives you that the result has some uncertainty, but not it's not maximum because the probability is not equal. One of the team is stronger, so it's more probable that that team would win. 0.8% probability that that team would win. So this way, this number entropy gives you information about the degree of uncertainty, and we compute this number by this expression. We compute this number by this expression, the source entropy. So let me discuss this binary entropy case. If you have a binary entropy, if you have a case of binary entropy, it means one of the two events may occur, right? One of the two events may occur. So if you assign your alphabet in case of binary entropy, just you have two alphabets in the set, right? You have two alphabets in the set. Two alphabets, which you can say that okay, one alphabet is x1, one alphabet is x2. So in case of a binary entropy, right, you have two alphabets, and you can say that there are it's a random source, and the random source has two possible outputs, x1 and x2, right? You can just model it as a random source, and it has two possible outputs. Now x1 has the probability p. Then because it's a binary case, the other one would have a probability 1 minus p. Now if you write the entropy expression, if you write the expression of entropy using that equation for x belonging to this, all members of this set, we need to compute p of x and log to the base 2, log p of x to the base 2. We need to compute this, right? So let's do it for this simple basic set. If we want to compute it for this one, it has just two summations, and the one would be probability for x1, probability of x1, and log p probability of x1 to the base 2, and the other term is probability of x2 and log 2 probability of x2, right? So these just two summations. So if you observe it, you already have these probabilities. So this is p and log 2 of p plus 1 minus p. We already have assigned these probabilities, and log 2 1 minus p. So if you further write it here, you can say that okay, the probability can be minus p log of p to the base 2 minus 1 minus p log of 1 minus p to the base 2. So this is the binary entropy when the alphabet has only when the set has only two alphabets, and we denoted by hb of p. So this h of x is actually denoted by hb of p for binary entropy. So the binary entropy in case of two alphabets comes out to be equal to minus p log of p to the base 2 minus 1 minus p log of 1 minus p to the base 2. So this is the case of binary entropy, and you would see that actually in entropy, this number which is computed, this gives you the minimum number of bits required for each source output. So this gives you the minimum number of bits required for each source output. We'll see this with the help of some examples, and it actually gives you the lower bound over compression also. You are familiar with the compression. You usually you try to save your memory by compressing your file and saving it in the hard disk, right, or in your smartphone. So compression is important, and we would see today how the compression takes place actually. And this number would be the lower bound over the compression, because it would tell you you need at least these number of bits per source output. You need at least these number of bits to store each letter of the alphabet. So this is the you can say this is the lower bound, or any compression techniques, different compression, there are different compression techniques, and they cannot do better than this number. This is actually the lower bound. If they achieve this HB, H sub B of B, it means that is one of the best compression technique. So we would see with the help of an example how actually the compression takes place in the compression takes place, and we would see this with more we would see this entropy in more detail. Similarly, you can talk about the entropy of a system which has like Urdu language. If you talk about the Urdu language, you have many texts, and if you think about the set, if you think about the set X, so this set X, in this set X you have these alphabets, right, up to Ya, and altogether these are 39 alphabets in Urdu. So if you try to find out how many by surveying different textbooks, if you find out what is the probability of letter alif, right? So you can say the probability of you just represent it as alif. Okay, I'll write it, probability of alif, and you have some number. Similarly, you can find the probability of the second letter. You can find the probability of other letters, right? You can find these probabilities, and you can find the entropy. You can find the entropy for this language. We usually say that we denote the random process by random variable x, right? So it is actually, we say the entropy is because the source is modeled as a random process, or we can say it appears as a random variable. So the entropy is dependent upon the source, is the function of the source. So we denote, we use this function, and the number, whatever the number you get, you that number, suppose you get some number, suppose 2.5, suppose you get some number 2.5, it means this is actually bits. The unit is bits per source output, So the source has these, one of these 30, the source has usually these 39 outputs, possible 39 outputs, and each of these outputs would require 2.5 bits of memory, right? So if you have 1 million in a textbook, you have 1 million of these outputs, 1 million of these outputs, and each of the alphabet needs 2.5 bits. You can compute the total memory required for storing 1 million of these alphabets, 1 million of these alphabets. So this way the entropy is important. It gives you the it gives you the measure of information, or in other words you can say it gives you the degree of uncertainty of the events, So we will see more examples with the help of Huffman coding, which is one of the compression techniques used for in the compressing your files.